Hey guys, so as I said in method 0, the general discussion, we have 4 different options for solving systems of equations. And the first of the 4 is what we're going to do here, substitution. And substitution is a very reliable way to solve, and like it's exactly as the name says, which is like you substitute in one equation with a variable from another equation, right? And so I'm going to show you exactly how to go about it in each of these 3 examples. But yeah, like substitution, as I said, works all the time, and therefore you could use it, on any kind of problem. I think that like if you get a system of 2 equations and 2 unknowns, then a quick way to identify if it's ready-made for substitution is to see if either of the equations has a coefficient of 1 in front of one of the variables. So like you look at the first equation and we're looking for a coefficient of 1, and that's a 5 there, that's a 2, no good. And we look in the second equation and that's a -2, but that there is a 1. It's not written, so it's a 1. So this is a way to identify that substitution is probably the most efficient way to solve this equation. And again, this kind of diagnosis is only true for systems of 2 equations and 2 unknowns. Yeah, so for example here, there's a coefficient of 1 right there, but that doesn't really tell us if substitution is the most efficient way to solve here. In fact, for a system of 3 equations and 3 unknowns, I tend to prefer either Kramer's rule, our last method, or method 4, which is an augmented matrix. And by the way, in each of the 4 methods, I'm going to use these same examples. Yeah? Okay, cool. Now, all right, so let's get on with it. Here it's substitution. Let's get on with it. So this is the first problem. All right, so as I said, that coefficient of 1 in the second equation tells us that we should use the second equation, and in particular, use the second equation to isolate y, which is to solve for y, because that's what we're going to substitute. So our second equation, which I'll write in like green or neon, whatever this color is -2x plus y is equal to 11, right? Now from here, it's clear that y will have to be 11 plus 2x, or 2x plus 11 if you fancy that more. Anyway, here we've used the second equation and isolated y here. So what we're gonna do is, first, note this equation and this equation are identical, but for our purposes, we prefer this version. So what we're going to do is get rid of the original second equation and only keep the modified version where we've isolated one variable. And then what we do is we take this new version of our second equation and use the knowledge that y is in terms of x and constants, which is that y is 11 plus 2x, to come in here and replace that y with 11 plus 2x. So the name substitution, because in the first equation, we are substituting for y with what we know it equals based on the second equation. We know, based on the second equation, that y equals 11 plus 2x. So we're going to go to the first equation, and very important that when you substitute into the unused equation, that is the unmodified equation. Yeah, so we're going to replace this y with 11 plus 2x. If for some silly reason you took this, which is the same as the second equation, and replace this y with 11 plus 2x, you're going to get a silly statement like 0 equals 0 or 11 equals 11. Yeah, so important that you substitute in the other equation. Anyway, you get it. So 5x plus 2, and then y right there, that y is 11 plus 2x based on the second equation. So 2 times 11 plus 2x. Just making it very clear that we've substituted for y using the second equation. and then equals 4. Cool. And so now it's 5x, and then plus, we have to use a distributive property here, there, and there, distribute, right? So 2 times 11 is 22. So 5x plus 22 plus 2 times 2x is 4x. So that, all this equals 4. Cool. Now we see that these are like terms, and we can combine them specifically to a 9x. So we have 9x plus 22 is equal to 4. And now what we're going to do is subtract 22, right, from both sides of this last equation we wrote. And when we do, we can write 9x equals negative 18. Okay, and now we can divide by 9 on both sides. And doing so, we can write that x equals negative 2, right? Okay, 18 divided by 9 is 2, and then we have the negative sign, so x equals negative 2. Cool, so that's how we solve for x. And now it's fairly easy to solve for y, because we already use the second equation to create a nice relationship between x and y, specifically that y is equal to 11 plus 2x, as I have written there. So this is x, and y is going to equal 11 plus 2x, so 11 plus 2 times negative 2, and that is y is going to equal 11 minus 4, which is, I believe, 7. Yeah, right. Okay, cool. So y is 7 and x is negative 2. And of course, you know, these aren't just like y and x values. They are a pair of coordinates, right? So negative 2 comma 7, which is the point of intersection of this line and this line. And we talked about that in method 0. We talked about what solving systems means visually and all that good stuff. So this here is the point of intersection of these two lines. Yeah, cool. All right, and the xy plane. All right, cool. Let's go to the second equation. Now the second equation, the second systems of equation, or system of equations, whatever the proper grammar is. But yeah, this guy here, right? So this isn't ready made for substitution, right? Because like there's no coefficient of x or y that's 1. So like when I'm confronted with that, I often go with elimination, the next method we're gonna learn. So here, really, like, you know, it's not, you know, super convenient for substitution, but it's not super convenient for elimination either. I just think that, you know, if none of the coefficients are 1, that elimination is like the way to go. And I think I think there's, I don't know what the precise reasoning for preferring it, but yeah, I think it should be preferred. And that's my answer, because anyway, if you wanted to do substitution here, what you would do is pick either of the two equations, which are equally convenient or inconvenient, and then solve for one of the variables, and then proceed as we did when we solved the first system of equations, which is substitute, once you've isolated one of the variables in one of the two equations. All right, so I guess this is kind of random, so I'm going to choose the second equation and solve for x using the second equation. So we've got 5x minus 3y is equal to negative 14. And so then 5x would have to equal negative 14 plus 3y, or 3y minus 14, whatever you like. And then x would have to be, well, my next step would have been to isolate x. I would have had to divide by 5 here, and therefore divide by 5 there. So x will have to be negative 14 over 5 plus 3 over 5y. And I guess now I have a justification for why I prefer elimination, because I don't really have to deal with fractions as much if I did elimination, right? Like, this is not a fun x to plug into the unused first equation. The first equation would say like 7x, or it says 7x plus 2y equals negative 1. So unfortunately, what we have to do, it looks like, is we have to take this here, specifically the right side, and replace that x with this, and that's like not fun. So like, yeah, I would do elimination, and I'm gonna use the same example 2 here in the video for elimination, so you can see how to do that. But I just showed you what the next step looks like for substitution, and it is again to write, I'll color code correctly as I did in the first example, but yeah, to write 7 times, and then we just learned x is this junk, so we'd have to write 7 times negative 14/5 plus 3/5 times y, and then you'd have to write, I don't even know that you needed to see this, and then plus 2y equals -1. So from here, yes, have fun and do the appropriate arithmetic / algebra, and you're done. So I'm not going to finish this past that. All right, so let's move on to the system of 3 equations and 3 unknowns. Okay, so let's move on to the system of 3 equations and 3 unknowns. And just like we did here, what we look for are coefficients of 1, which are like right there, and even the coefficient of -1 is useful when we don't have coefficients of 1, but we have 2 of them, so we're good. And between the 2 choices, the first and second equation, let's go with the first. And there, in the first equation, which is 4x minus 3y plus z equals -10, let's solve for z. And if we do, we'd have to write the z is equal to -10 minus 4x plus 3y. Okay, cool, nice. So now notice this equation and this equation are identical. It's just that here we've isolated z. So let's take the isolated z version of this first equation and use it to substitute for z right there in the second equation. Right here, that was faint, and then right here, yeah? Cool. So notice that we've used the first equation to isolate z, so we can't substitute back in there. So we have to substitute in the other two. And what we're substituting for is z. So we've got 2x plus y, and then plus 3 times z is -10 minus 4x, and then plus 3y equals 0. Right? That's the second equation with z substituted with what it equals, namely this stuff. Okay, and then we do the same in the third equation, substitute for z, and that's -x plus 2y, and then it's minus 5 times z this time is what it was before. Alright, here we go. Now, do you notice that the second and the third equations are now entirely in terms of x and y? Look in the 2 equations. There's no z, obviously. We got rid of it. So, and that's the whole point of this solving for one variable in one equation and plugging it into the other two. What it does is it takes a system of 3 equations and 3 unknowns and turns it into a system of 2 equations and 2 unknowns, which we know how to solve. We solved 2 equations and 2 unknowns fully here, and I showed you the start there. Right? Okay, cool. So now let's simplify these 2 equations a little bit. And I guess to break the monotony, I'll do it in a different color. So we've got 2x in the first equation plus y. And then we've got, that's -30, distributing the 3, right? And then we've got minus 12x. And then we've got the plus 9y. And the right side still equals 0. Yeah, cool. And then the second guy says minus x, right? And then plus 2y, that's just a start. And then the distributing says plus 50, okay? And then we've got plus 20x, right? Plus 20x, okay? And then we've got minus 15y equals 17. Got it. And of course here we can do some combining like terms and all that good stuff, and write this equation in green or neon in much more succinct way. For example, 2x and negative 12x make a negative 10x. So we've got negative 10x, and then that's those two taken care of, and then y 9y make positive 10y, and then we've got minus 30, but I'm gonna take the 30 to the other side and write equals 30. Cool. And then the second guy, this guy and this guy combine to 19x, right? And then the y's, what about them? These two make a, so let me cross out the x's first. That's it, 19x, and then this guy and this guy, the y's make a negative 13y, right? Equals, and then it's gonna have to equal 17 minus 50, right? And what is that? Negative 33? Yes. Now, none of the numbers involved in this 2x2 system look appealing. Like, look at that, 19 and 13, prime and ugly and all that good stuff. But you can actually solve this system, and it should work out nicely. And here's actually something you could do about it immediately. Noticing that you could divide both sides of this by 10, you could just reduce the first equation to negative x plus y is equal to 3. And immediately, like, you've got yourself a nice equation. In fact, we can write y minus x instead of negative x plus y. But yeah, this equation and this equation are identical, right? They have the same set of solutions, and they're the same line. So you could write that instead, and now it's like a bit more pleasant. 19x minus 13y is the second equation. You can't really do anything about it. Equals negative 33, and then go from here. I know for a fact that when I chose this set of equations, that you get nice numbers. They're integers. You get a lattice point. So all three answers are integers, and that's what a lattice point means, by the way. Integer coordinates. Anyway, yeah. So because I know it works out nicely, like, I'm just gonna let you finish. But obviously, like, you can finish by substitution, and why not, since we're on it? And what you would do is, like, in this first equation, for example, solve for y, and you'd get y is equal to 3 plus x, right? And then you take that and you replace this y with 3 plus x, so you've got 19x minus 13 times 3 plus x equals negative 33. And of course, that's this equation, once you simplify it and solve for x, will get you x, and then you can come back here, get y, and then of course we went this path by knowing that z from the first equation equaled negative 10 minus 4x and then plus 3y. So if you get x through this and then you get y through this, well, you've got x and y, and therefore could get z. Yeah, okay, could get at z. All right, sorry about the stutter at the end. Okay, cool. This is it. Yeah, and yeah, the other 3 methods to come, and yeah, so keep watching. Take care.